All right, hello everyone. Well, I'm going to give a little bit of an update on our Wolfram Physics project and then turn this over to Q&A and discussion about the state of our project. We first launched this project to the public in April of last year, and lots of things have been happening since then. I would say things have been going spectacularly well. The thing that's perhaps to me most remarkable about the project is the extent to which the things we're figuring out about physics also inform other fields, and the extent to which we're able to use ideas from other fields back in physics, and the extent to which we're able to use ideas from other directions in mathematical physics for our project, and the extent to which those other areas in mathematical physics can benefit from things we're figuring out in our project. So we actually just wrapped up at the end of last week our winter school. We had a summer school last summer. Now this beginning of January, we had a winter school, which was, we had about 20 physicists there working on all kinds of different projects. And maybe we'll talk a little bit more in detail about those projects a little bit later here. I think the big summary was, these are mathematical physics projects, basically, all working towards kind of connecting the ideas of our physics project to all sorts of different directions of mathematical physics. And seeing, I think the thing that I'm realizing is what we are providing is sort of a machine code for the mathematical physics of our universe, so to speak. We're providing kind of this very concrete low-level representation of how things in the universe can work, and a lot of kind of fancy ideas about mathematical physics can live on top of that, whether they're ideas about just sort of discrete differential geometry and its limits, whether they're ideas about things in group theory, whether they're ideas about the way that certain features of quantum mechanics work, and so on. These are all things that can kind of live on top of our basic models. And I think the other thing I'm sort of realizing is that many years ago, in the 1980s, I started working a lot on cellular automata, which are kind of minimal models of systems that have a sort of a built-in notion of space and time and a built-in set of discrete states. Cellular automata have turned out to be models of a spectacular range of kinds of things in the world. In a sense, the simplicity of those models made it possible for them to be this sort of underlying stuff of lots of different kinds of things that one wants to study in the world. Well, similarly, in our physics project, the fundamental models that we have based on these rewritings of hypergraphs, they turn out to be a sort of fundamental model of lots and lots of kinds of things. Not only things about the physical world, things I'll talk about a bit more in meta-mathematics, things in distributed computing, things probably in chemistry, things perhaps in biology, lots of different areas. The same sort of underlying model where we have sort of the minimal model of discrete asynchronous things happening and the connections between them. These models that we've developed for physics work in those cases. And the thing that's interesting is we're able to leverage the things that have been learned in 20th century physics, particularly general relativity, theory of gravity, and quantum mechanics. We're able to leverage the things that we've learned there to make progress in thinking about all these other kinds of areas. And we're also able to import intuition from those other areas back into thinking about physics. So we might refer to some kind of thing that's happening in physics as being like a lemma, which is something that comes from mathematics. Or we might say that something is like a eventual consistency of a database system, something that comes from distributed computing. But then we might also take the kinds of things we think about in physics project about thinking about understanding the universe in terms of reference frames and so on, and import that into thinking about distributed computing and those kinds of things. So sort of very fertile set of communications between these different fields. I would say also that something that's happened in the last few months is sort of an increasing integration of some particular areas of mathematical physics, well, like causal set theory, for example, with the kinds of things that we're doing, sort of a greater understanding of how to think about our models, think about what our models do in terms of what's happening in causal set theory, think about causal set theory as informed by our models and so on. Also in areas, in sort of more mathematical logic areas, thinking about term rewriting systems and the mechanics of term rewriting systems, informing those with ideas that come from our models, like ideas of causal connections and so on. So in any case, those are some of the kinds of directions that that things are going in. Now, I'll mention a few sort of general areas and general realizations. One thing I might say is people say, well, when is this going to connect with experiments? When are we going to be able to do an experiment and see the effects that we're talking about in these models? Well, it's always a challenge from two sides. It's kind of like go from the model and kind of build out to what is experimentally observable, go from what's experimentally observable and figure out how you can see things that are relevant to the model. I'm about to try and do a big project of sort of looking at the phenomenology of our models. And it's really a kind of creative activity, because both in terms of cosmology and general relativity and the large scale structure of space-time, and in terms of quantum mechanics, and in terms of sort of mixtures, in terms of black holes and things like that, there are effects that one can imagine in all of these places. And it's a question of figuring out which ones are most likely to be accessible to actual experiments. So for example, in terms of the large-scale structure of space-time, one of the things that's very unique in our models is this idea that the dimension of space doesn't have to be exactly 3, that there can be fluctuations in the dimension of space, the areas where space is effectively 3.01 dimensional and so on. Particularly in the very early universe, we kind of imagine it's likely that space was very much higher dimensional, effectively, than it is today, that it's sort of, at the Big Bang, space was sort of infinite dimensional, it gradually cooled down to be 3-dimensional. What kind of relic dimension change can we detect? To what extent is it possible, for example, to see photons that have come from the cosmic microwave background and see that they have traversed some area of varied dimension, and what consequences would that have for them, and can that be observed today? To what extent is it the case that we can understand phenomena in sort of cosmology, large-scale structure of the universe, in terms of things like dimension fluctuation? We don't know how big the dimension fluctuations are. That's a whole very complicated calculation that may depend on the details of the underlying rules. I mean, I should say that one of the other things that's come out that I didn't completely see coming, I did to some extent, I suppose, is the following fact. There's a framework in our models that involves this idea of a spatial hypergraph, these rewriting rules on the spatial hypergraph, the kind of computational irreducibility of that rewriting process. There's kind of a framework of all of those kinds of things. And the question is, do you have to understand all the details of all those individual rewritings and all that sort of computational irreducibility to say things about the universe? And the realization is, no, you don't. There are certain sort of pockets of reducibility that you can identify in the universe that don't depend on those underlying details. It's essentially the same phenomenon as the very dramatic, but still not completely mathematically physics understood phenomenon in fluid dynamics, where you start off with these discrete molecules bouncing around, and you end up where it's very hard to describe all those individual molecules bouncing around, but you can end up with this continuous fluid whose features can be much easier to describe. And it's somehow the interest these days in hypersonic vehicles reminds me of the fact that back in the 1980s, when I worked on using cellular automata as a model for fluid dynamics, that was something that that one could make the sort of smooth transition to those kinds of flows in the case of cellular automata. And I kind of do wonder whether there are things that can be done with our new models that would be a way to think about those kinds of things for fluid flow. But let's put that aside. But in any case, the fact that fluid flow has this sort of collective fluid behavior, even though the molecules at an underlying level can be quite different. They can be air, they can be water, they can be something else. It's the same story with our models of physics, that the underlying rules can have all sorts of detailed different forms, but nevertheless, the large-scale structure can show these sort of reducible features of things like general relativity. Now, one of the things that talking about just recently is the concept that the question is the fact that it's possible to have a sort of continuum description is a consequence of the fact that there is this computational irreducibility, which leads to a certain kind of level of randomness or apparent randomness in the underlying behavior of things. And that's what allows you to kind of take averages and say the aggregate behavior is like this. But one thing we thought was sort of an independent kind of feature of what we think about the universe is that it is both has this computational irreducibility that leads to this effect of randomness, and it's ultimately finite dimensional. And it has ultimately, the way that you can describe space is as something which has sort of locally behaves or reasonably locally behaves like a sort of a manifold with a finite number of dimensions. What we realized recently is that actually that second condition about finite dimensionality is actually really no different than this sort of computational irreducibility story. Basic point is that if you were going to have that in order to describe the system, you have to have some kind of foliations, and you have to have some way of describing those foliations. And in a sense, to say you have an infinite dimensional space is to say that those foliations are somehow sort of infinitely complicated, that they have in order to have a foliation that can possibly make sense, you have to have identified a sort of piece of reducibility in the system. But to say that it's infinite dimensional is effectively to say that there aren't going to be foliations that are finitely describable in a way that we can sort of, that makes sense, so to speak. So the very fact that the universe, that it's possible to identify, to have sort of an observer who thinks the universe makes sense at all, is kind of implies in some sense that the universe has to be finite dimensional, and the fact that you're sort of set up for the universe that isn't finite dimensional being sort of undescribable that way is then a consequence of this computational irreducibility phenomenon. So in any case, so one branch of what I'm about to start working more seriously on is sort of the phenomenology of how can we observe features from our models in large scale and the cosmological scale and small scale and quantum mechanics and sort of the intermediate case of black holes, things like this. Some of these things may be very, very far away from what is conceivably experimentally observable, and some may turn out by luck or whatever to be things that, oh yes, we actually can see that in our universe with actual experiments that we can do. So don't know exactly how that's going to come out. Now, another big direction has been sort of in the relation between our models and existing physics is how do we know that we are reproducing general relativity, for example? How do we know that we're reproducing quantum mechanics? Well, we think we have proofs of these things, but the proofs depend on certain assumptions which are not particularly embarrassing assumptions because they're the same assumptions people have had to make to use statistical mechanics and to derive things like fluid mechanics from molecular dynamics. A dirty secret of that business is there isn't really a completely rigorous derivation of those things. The reason, I think, is because those things are deeply tied into computational irreducibility, principle of computational equivalence, and so on. They are kind of, and they ultimately rely on things like computational boundedness of observers and so on. They involve kind of a whole story of mathematical logic and kind of thinking, computational thinking about the fundamentals of mathematical physics that really hasn't been possible before. Maybe we're going to be able to do that now. But that's something that, so when we say we can derive the Einstein equations, yes, we can do that in the same sense as one could derive something like the fluid equations from molecular dynamics. It's pretty good, but there's can we say it's a formal, complete mathematical proof? No, because we're running into computational irreducibility and so on in the middle of the whole thing. So the way that we can empirically determine that we're doing a good job is by saying, okay, let's actually simulate our models. Let's actually sort of take computational irreducibility at face value and just do the computation and see what happens. Well, now the question is, can we make a bridge between what people normally observe with general relativity and the Einstein equations and what happens in our models? And so this is an interesting thing. Jonathan Gorard has been particularly working on this of late, trying to use our models as sort of explicit, concrete models to do actual calculations in general relativity. So, just to recap on how that's normally done, you're studying the merger of two black holes. you have these Einstein equations, which are these complicated sets of partial differential equations, and you say, these Einstein equations are true. Now let's figure out how we compute from them using a computer. Now, some part of the computation can be done algebraically, usually done using Mathematica and so on. Some part can be done algebraically, sort of exactly in terms of the equations, but you reach a point where you say, well, we've just got to do a numerical computation. When you reach that point, you have these continuous partial differential equations that you're doing this with. Those don't sit well with computers. You have to discretize those equations. You have to use sort of finite element-like methods. It's a very difficult case of using those kinds of discretizing methods because there's a lot of freedom to do with kind of how you foliate space-time and things like that you have to fix in order to have a definite way of doing that discretization. So one of the things Jonathan has been working on is can we go the other way? Instead of starting from the Einstein equations and discretizing and ending up with some kind of approximation that we got from numerical analysis, can we say, just start from our models at the lowest level, at the 10 to the minus 100 meter level, and just have a whole bunch of our little discrete hypergraph elements, and then just say we've got enough of those that we can get a good approximation to this sort of continuum behavior. We've got enough of those, we sort of treat them as not being quite as small as they really are in practice. But we've got enough of them that we can sort of take a continuum limit in our actual computations. And so the goal there is to reproduce the actual calculations done in general relativity and be able to see those things. And maybe we'll talk about later, maybe Jonathan could show some examples of actually looking at things like Kerr black holes, rotating black holes, and seeing what actually happens in the spatial hypergraph to one of these things, and seeing little pieces, singularities and little pieces separating off and becoming disconnected. These are things that you just can't see in the continuum, in the sort of continuum model of space-time, but you sort of do in effect see them in these numerical analysis discretizations of the Einstein equations, but that's just numerical analysis. What we're seeing now is coming from the genuine physics, coming up from kind of the machine code. So that's sort of a thing in general relativity, and I think we sort of are talking about it as proof by compilation. If we can take the actual problem of merging black holes and we can show that we can get the same results, we can get the results that are actually observed experimentally there by doing calculations directly from our models, that's a really good way to validate that our models are really working right. Well, in quantum mechanics, same kind of story, a lot of work with categorical quantum mechanics and ZX calculus as a formalism for quantum mechanics, and showing the direct formal connection with our models, and ultimately a way of compiling sort of quantum information theory computations directly into multi-way computations. And it's looking like, and this is another thing Jonathan's been working on particularly along with Xerxes and Mano, the question of the kind of, when you do this compilation from sort of standard quantum, sort of a standard quantum mechanics representation into our multi-way graphs, you immediately get sort of, you immediately sort of are exposed to a lot of technology from automated theorem proving and so on that you can make use of. And so there's the question of using that to more efficiently than people have been able to do before, actually do computations and make predictions in quantum mechanics. So that's another kind of thing that's been going on. So I would say another direction in our physics project is sort of climbing up the tree of mathematical concepts and so on. And let me describe what I mean by that. So we have this big hypergraph, and the first thing is, does it behave roughly like a manifold? Does it roughly behave like continuous space? That's something we looked at. Does it, how do we define vectors in such a situation? How do we define things like, I don't know, tangent bundles? How do we define fiber bundles? How do we associate, how can we, so in physics, as it's been done in the past, one of the big ideas is local gauge theory. So in local gauge theory, there's a base space that is kind of the space-time, the usual world, the usual manifold of space-time. And at each point in space-time, there's a fiber of a fiber bundle. And that fiber has sort of internal degrees of freedom that represent things like the sort of the color charge or something like that, or that are associated with these different internal symmetry groups and so on. So there's a question in our models, everything in the universe is just made from this hypergraph. And all features of the universe, including both the external space-time and the internal degrees of freedom, all have to be features of this hypergraph. And so one of the things, and we looked at several people at our winter school looked at this, looking at kind of how to think about things like fiber bundles in the context of our discrete models. And it's looking to be incredibly beautiful. I mean, it's looking that really what's happening is you can kind of decompose all the sort of complexity of these kind of our evolving hypergraphs, and you can start decomposing that into pieces that you can think of as being parts of the base space and parts of the fibers. And we need to work more on this. This is a big direction, and I think that direction is going to lead us to really understand a lot more about particles. One of the things in our models, there's this kind of spatial hypergraph. What are particles? Particles are some kind of topological obstruction in the spatial hypergraph, some kind of lump of stuff in the spatial hypergraph that is somewhat stable to the overall evolution of the spatial hypergraph. There's sort of the background of space that's bubbling around, and there's this kind of lump, this thing like a vortex in a fluid or something that has some degree of stability with respect to the other things that are happening. But one question is, can we characterize those kind of lumps? And a way to characterize those lumps is using these ideas of fiber bundles and local gauge invariance and so on. And the thing we know about the universe is that there is some local gauge invariance that's associated with the standard model of particle physics, that's associated with these Lie groups, these continuous groups, things like the rotation group that gives you the sort of continuous rotations you can make in space. There are generalizations of that. The one that shows up in particle physics is SU3 cross SU2 cross U1, which is a subgroup of, for example, E7, one of the exceptional Lie groups. The thing that we'd like to know is, given the spatial hypergraph, how generic is what kinds of continuum limit of groups? We can say, well, something like an interdimensional space is not generic, but it can happen in our hypergraphs. Is it that a local gauge group like E7 is something that can happen? Is it generic? Do you always get some subgroup of E8, or what do you get? And I think that's a direction to go in. And I think that as we start to understand sort of a big story is the story of homotopy and holonomy and so on. If you go around loops in our spatial hypergraph, you go around a loop in the graph, and you ask sort of what happens in these loops, and to what extent can loops be deformed to nothing, and to what extent do they have sort of obstructions to their deformation to nothing? Those things and kind of what happens as you go round a loop, those are stories that probably relate deeply to stories about quantum numbers, things like spin, things like the internal quantum numbers associated with local gauge invariance and so on. These are things that we hope to investigate a lot in the coming months. So that's one sort of mathematical physics direction. I would say one thing that was particularly fertile at our winter school, something that Jonathan had done in connection with causal set theory. So in causal set theory, the idea is, we've already got a space-time. We've already got the notion of four-dimensional space-time, for example. But we say, but we don't know, but we imagine that somehow things are discrete. We've got this background, but we imagine that what actually exists in the universe is discrete. And so we kind of populate that background with a bunch of points in space-time. And these points, you just sprinkle these points into space-time. And then you say, all that the universe, all that physics depends on is the causal relationships between these points. And those causal relationships are defined by where those points are in space-time. So as you have a certain distribution of those points, you'll build up this causal graph, this partially ordered set of events in space-time, this partially ordered set of sort of points in space-time. You'll build up this partially ordered set, and then you can ask about its properties. And you can ask, for example, when does it show Lorentz invariance, etc. It's all been a bit mysterious in causal set theory, because people just saying there is already a background structure of a place to put these points. Let's just sprinkle these points down in some way. Well, there are particular statistical distributions of point sprinkling that have nice properties like Lorentz invariance and so on. Jonathan wrote a paper recently showing that in what our models do is to provide an algorithmic basis for that sprinkling procedure. They tell you how to do that sprinkling, and they tell you how to do the sprinkling, actually independent of having a base space to operate in, but they tell you how to do the sprinkling in such a way that you're guaranteed to get Lorentz invariance. You're guaranteed to have relativistic invariance. So, but one of the things that work did was provide a way to say, let's sprinkle not on flat space, but let's sprinkle on a space that corresponds to, let's say, one of the known solutions in general relativity. So this kind of gives a bridge between sort of this existing solutions to the Einstein equations, which there are a modest number known, and what happens in our models. Now, in a sense, by that kind of sprinkling, you're not being as general as we can be in our models, because, you know, Einstein's equations operate just in 3+1 dimensional space-time. Whereas in our models, you can have changes in dimension, you can have all kinds of sort of topology change and so on that would be quite impossible in these continuum equations. So, okay, so that's a little bit on those kinds of directions. I would say that the thing that I think some of the next breakthroughs are likely to come in thinking about kind of the mathematical physics of fiber bundles and the mathematical physics of sort of cycles and graphs and so on, and that's where we're going to see sort of the next level of connections to the physics that we know. I mean, again, the big surprise of this project has been that it's possible to kind of see this computational reducible features, which are features of of physics as we know it, of 20th century physics as we know it. To be able to see those generically from our models. And the question is, how far does that go? Are local gauge theories another generic feature? I'm guessing yes. Can we use the ideas around that to kind of probe things which like the existence of quantum numbers and so on in our models? I'm guessing yes. It's just hard work. It's difficult mathematical physics. It's a very interesting thing to try and generalize the ideas of mathematical physics and the ideas of things like differential geometry to discrete differential geometry. Was a project at our winter school looking at sort of the generalization of differential geometry to the discrete case. And I think Jonathan has a whole collection of things that are turning into Wolfram function repository functions for Wolfram language that are supporting all sorts of discrete differential geometry. I mean, I would say that it's kind of, you're kind of relearning calculus. It's kind of like, what is a plane? What is the notion of a tensor? What is this kind of thing? How do you define these things? And how do you define them in not only in these hypergraphs and in fractional dimensional space? Normally, you have something like the Riemann tensor, which measures the curvature of space. That's a four-legged tensor, four-index tensor. Each of those indices, let's say in 3+1 dimensional space-time, runs over 4 values. It's difficult mathematics. It takes lots of computational effort to deal with it, but it's been something that has fundamentally been understood for 140 years or so. And calculus in general is a story of variation of quantities in interdimensional space. We have a generalization of that where we're dealing with these hypergraphs that can limit to fractional dimensional spaces. How is that dealt with? I think we're slowly beginning to understand that. We're slowly beginning to understand what is underneath vectors and tensors. How are vectors and tensors built up? Just as space in our models is built up from these discrete underlying sort of atoms of space connected in this hypergraph, and in a large scale limit, it behaves like continuum space. How do things like tensors get built up from a lower level machine code? And what we're beginning to understand is things like that tensor index, the R mu nu, whatever it is, the mu and the nu. Those indices represent kind of equivalence classes of lots of of a whole direction of things, a whole family of geodesics that are going in a particular direction, in some sense of direction, which we also have to define in our hypergraphs. We're kind of compressing all of those into saying, oh, it's just one index. What's really there is something where there are individual points in the hypergraph, but they're being conflated into just being represented in terms of that index, much as we can say when we talk about some kind of manifold, we can say, well, there's actually a bunch of individual points there, but we can conflate that all into just talking about this continuous space with these dimensions of space. So it's sort of the same kind of thing, but we're slowly understanding, what is a fractional dimensional tensor really, and how do we set up all of those kinds of constructs? So it's kind of calculus as it's existed is about 300 years old. And, we get to build a new version of it that's built from sort of lower level primitives. And it will not be the same as ordinary calculus. It is a generalization. And I think it has very, very fascinating mathematics associated with it, which is just beginning to be explored. So let me mention a couple of other things, and then we'll turn this over to more discussion. I bet Jonathan has things that he would like to say here as well. So, but let me talk about a couple of other kind of directions here. So another big story, which I kind of alluded to at the beginning, has been the connections of our model to other things, not even in physics, and how we make those kinds of connections. I got a bit distracted actually last few months on a couple of those directions. I mean, one was a kind of a footnote in my New Kind of Science book about the theorem network of Euclid, which turned into a big long post. And then I got very distracted on the 100th anniversary of combinators, sort of the most foundational, in some sense, the very simplest model of symbolic computation, which we've almost been able to use all of in Wolfram language over the years, with the exception of the one idea of there are no named variables, which I think is not particularly friendly to humans and not so suitable for a computational language intended to be used by humans. But I think that those two studies led me to all kinds of other correspondences of different kinds of things with our physics project. And it's sort of interesting, having thought about, for example, things like combinators in the past, having the methodology from our physics project just greatly informed what one could think about in terms of combinators. I mean, one of the things, combinators, so in some sense, our physics project is a story of transformations for certain kinds of symbolic expressions. We can think of our hypergraphs as being collections of relations between elements. The atoms of space are just these elements, these things that have nothing other than their identity. Then there are relations that are the hyperedges of the hypergraph, which just say this collection of 4 elements are related. Element 1 to 2 to 3 to 4. That kind of notion, we can think of that as a kind of symbolic expression that is a collection of sort of n-argument objects all collected together in this big orderless list. So it's a special kind of symbolic expression. And in a sense, we can think of the evolution rules in our models as being transformation rules for patterns associated with those underlying expressions. Well, we can generalize that and we can say, well, what about more general expressions? I mean, in Wolfram language, it's all about transformation rules for expressions that actually we know mean something, pluses and timeses and things like that. The sort of big idea, in a sense, that is from 100 years ago, from Moses Schoenfinkel and the invention of combinators, is this idea of you can have a purely symbolic expression, and that purely symbolic expression, sort of in his rendering, it's just made in his case from S's and K's, which only import from the outside the things that have meaning. But you can also think of that in terms of you can say, let's use the infrastructure of symbolic expressions without any meaning. There's no plus, there's no times. It's just completely, it's just this thing that's the head of the expression that is just, an element with some identity. So anyway, that's kind of the notion of combinators. It's sort of a generalization in some ways of what we imagine the spatial hypergraph of our universe might be like. That leads one can look at all the kinds of things we can look at in our physics project. Combinators don't have a great notion of space. They have a good notion of what one can call tree-like separation, of things being these expressions nested one inside each other and so on. So in our physics project, we have the idea of events that happen being time-like separated. That is, an event happens and later in time another event happens. Or space-like separated, to be thought of as happening at the same time but at a different place in space, in the way that we define the notion of space and time with a particular foliation. Or we can say, when we think about multi-way systems and for quantum mechanics and so on, we can say that events are branch-like separated. They occur at the same time, but on different branches of this multi-way system that corresponds to the different possibilities in quantum mechanics. Combinators add another possibility for separation, which is tree-like separation, where one event can occur sort of higher in this expression tree than another. That's a very bizarre thing, probably not realized by physics, probably, unless there's some weird sort of scale relativity kind of concept that's happening in physics, we don't think that's what's happening in physics. But it's interesting to see that and to see the kind of whole methodology of multi-way systems and causal invariance and all these kinds of things play out in terms of combinators. Well, so one of the things that I said that there were these sort of connections to other fields. One big one that we've been exploring in different ways is the connection to metamathematics. So our multi-way graphs are very much like the networks that represent the proving of possible theorems in mathematics. So the rules, you have a particular state that corresponds to some mathematical expression. You have a rule that says how that can be transformed that represents some kind of axiom that you say leaves that expression equal. So, you know, x plus x, or x plus y is the same as y plus x. You can transform x plus y to y plus x in some expression, and you'll get an expression which is said to be equal. So then the sort of the multi-way graph of applying all those transformations, in a sense, the paths in the multi-way graph define all possible theorems, or when you look at two things which are connected by a path in the multi-way graph, they correspond to two things that must be equal, and it's a theorem that they're equal. And then the actual path you follow is the proof of that theorem. So that's kind of the correspondence between kind of our sort of multi-way graph type idea and something in mathematics. Now, in mathematics, it can get a little bit more complicated because sometimes you think about things not in terms of equivalence, equality of expressions, but more in terms of theorems that are true, where theorems can be derived from the sort of the basic notion of truth. You can derive a bunch of theorems. Then you have a multi-way graph that's a kind of multi-input multi-way graph where you'll have sort of a thing that's true and another thing that's true, and you'll be able to combine that to say, here's another thing that's true, a kind of meta-logic rules of inference that gives you sort of deriving a new true fact from previous true facts. So it's a slight twist on what's going on, and considerable technical difficulty associated with that slight twist. But kind of the idea is the possible theorems of mathematics are something like the possible paths in this multi-way graph where the rules are defined by the axioms of mathematics. And then there's a question, you know, when I was studying Euclid, he started off with 10 sort of rules, 10 axioms. He derived 465 theorems. He was in a sense exploring only a tiny fraction of the infinite number of possible theorems of geometry that exist and that are derivable from his axioms. So in a sense, one can ask the question, you know, there's a kind of a geometry of what that space of all possible theorems that can be derived, the metamathematical space of all possible theorems. Euclid is kind of exploring the human geography of which particular theorems are humans, or Euclid in particular, interested in identifying. And so there's this sort of question, what is this limit of metamathematics, this sort of infinite space of possible theorems? What does it look like? How do we understand its structure? And that's something where it's deeply informed by things we're thinking about in the physics project. And it's likely that some of the sort of meta observations of mathematics, things like the fact that mathematics is often doable and not full of undecidability all the time, will be a statement associated with the way that sort of multi-way graph gets explored. And so that there's questions about what does it mean? What is the bulk limit of mathematics? Just as we can say something about sort of the bulk limit of in physics, that is the kind of thing we perceive, what is the bulk limit in metamathematics? And how do we use ideas from mathematics of things like non-constructive proofs and so on? How do those come into what we think about in physics? Now, I might mention another thing, which is one of the fundamental features of a multi-way graph is many things can be happening in it. It's what is often called in theory of computation non-determinism. That is, you can have like a Turing machine where there is a definite rule for the Turing machine. It says for any state of the Turing machine, it tells you what the next state is. It's kind of one state to one state to one state and so on. But you can also have a non-deterministic Turing machine, a multi-way Turing machine, where one state of the Turing machine can have multiple possible next states. So actually, I've just very recently been studying quite a bit multi-way Turing machines. It's quite interesting, and there's all sorts of questions like, what's the simplest universal multi-way Turing machine? Back 15 years ago or something now, well, when was it? 20 years ago, I kind of identified a candidate for the very simplest possible universal deterministic Turing machine. And then a chap called Alex Smith in 2007 responded to this prize we put up and proved that, in fact, this particular Turing machine with 2 states and 3 colors on its tape is universal, and we know it's the simplest possible universal deterministic Turing machine. What is the simplest possible universal non-deterministic Turing machine? I have a guess, and it's really simple. It's kind of like, well, I've been studying this recently, and like yesterday and so on. But by the way, I might comment when I say I've been studying this recently, and if you're curious what I've been up to, we've been very open in posting sort of everything. So I think you'll probably find even today, you'll find the scratchings that I was making in notebooks last night working on this problem, and also a video work log of me, rather boringly perhaps, just working on making progress in this particular area. But in that particular case, there's even a question of what does it mean to have universality in this non-deterministic system? How do we think about that? This is, okay, so and why do we care for the physics project? Well, I'll tell you why we care. One of the things that happens is we have to think, well, okay, so when we think about quantum mechanics is a story of these multi-way branchings of many possible things happening in the universe. And there's kind of the question of what, when we think about kind of one of the big mysteries of kind of quantum mechanics is that people think definite things happen. Even though the universe is sort of branching in all these possibilities, people think definite things happen. How does that come to be? Well, what I'm increasingly realizing is that it's a complicated story. It's hard to get one's sort of head around it, but let me try and explain it a little bit. So let's talk about space-time, first of all. In space-time, you might say, oh, there are all these events happening in space-time. This one happens, then this one happens, and we can see from the outside what event is happening when, which event happens before which other event. But if we are observers embedded within space-time, we don't get to make that from the outside observation. All we know is that certain events, including ones inside us, are happening, and all we get to know is the causal relationships between the events that are happening, some inside us, some elsewhere, and so on. All we get to know is the causal graph that represents the sort of relationship between events. Okay, so now let's consider the quantum mechanical case. In the quantum mechanical case, the thing that we're imagining is the observer is embedded within the system. So the observer we say the system is branching. It's got all these different branches going on. Well, that means the observer's brain is branching as well. And so the question is, how does a branching brain observe a branching universe? That's kind of a basic question. How do we think about that question? Now, Jonathan, from very early in this project, actually was sort of a launching feature of this iteration of this project, came up with this idea about sort of an interpretation of quantum mechanics that's based on completions, based on sort of forcing there to be consistency, forcing there to be causal invariance associated with an observer who just imagines that certain kinds of things are equivalent. The observer just says, in order to keep my thinking coherent, I'm just going to imagine that this is equal to that. I'm going to, in the mathematical context, I'm going to invent a lemma and connect this to that. And in a sense, what I think is kind of going on here is in this kind of branching brain observing the branching universe, if you're a branching brain, how do you feel about the world, so to speak? In a sense, I think it's possibly an essence of kind of the idea of consciousness and so on, that we have a definite thread of consciousness. I mean, I've always kind of resisted the idea that we can have sort of a scientific definition of consciousness. I've always kind of tended to think that in the sequence of kind of life, intelligence, consciousness, it's even more fuzzy than life and intelligence, for which I believe there's really no non-historical way to define those things. They're just symptoms of sophisticated computation. But I've sort of begun to think that maybe consciousness is a little bit of a different story, and it really has more to do with the fact that one is kind of corralling experience into a definite thread. that one is not just imagining that all these different things are happening incoherently all over the place. One is imagining that definite things are happening, and that that's kind of the essence of what we mean by consciousness. And I think that it was pointed out to me that I'm not the first one to have thought about this. Immanuel Kant had a whole statement about consciousness being sort of something that integrates the manifold pieces of experience and so on. I never can understand these philosophers, but that's kind of a sort of it's good to know that the thinking about what might be going on is not so different. But in any case, so the question that one starts asking is, in this multi-way Turing machine that has all this branching behavior going on, if you are an observer of the multi-way Turing machine, what do you think about it? You're an observer who's actually a Turing themselves in the multi-way Turing machine. How do you sort of extract from this branching behavior this kind of consistent thread of what's going on? Now, why do we care? Well, so here's a reason why we might care. Let's say we're trying to do, we think about computation right now. We think about computation where there's an input, there's an output. It's kind of one input, one output. It's a function, f of x or something. There's an x that goes in, there's an f of x that comes out. Okay, now what happens if instead there's this branching multi-way thing, and what's coming out is this whole collection of different answers, all these different branches of possible answers? You know, how do we think about that? And I think that the way that we have to kind of that's so. And why do we care about thinking about that? Well, if we're doing distributed computing, we might much more naturally have this whole collection of answers than saying, oh, this was one definite answer. When we're doing quantum computing, one of the things that is the sort of essence of what has to be done in quantum computing is to corral all those parallel quantum threads into that one definite classical answer that you say, oh yes, the thing factored the number and it's this, and so on. So if we even imagine implementing computation at a molecular scale, for example, with chemicals, we are immediately thrust into this issue. So we're thrust into the issue of, you've got all these chemical reactions going on, you've got all these different, molecules made of carbons and so on, and you've got this whole network of reactions, and all kinds of different things can go on. And there's this giant network, essentially a multi-way graph of all these reactions. If you're a chemist who's doing synthetic chemistry, you're typically interested in the one path through this multi-way graph that produces the particular output that you want to have, and you want to get the largest path weight, the largest yield in that particular path. You want to kind of concentrate everything onto getting this particular result. And so that's sort of the traditional way of doing chemistry. But imagine that you're really confronted with, oh, you're just going to produce all these outputs. Can you think about chemistry that way? Can you think about using all those outputs for computation? Let's say, for example, all those outputs are all prime. Well, maybe it's useful to have a big bucket of prime-sized molecules, for example. Let's say, and that's a different kind of thing than saying the answer is some particular result. But how do you think about this? How do you think about composing computations that work this way? How do you think about those kinds of things? These are things that I think get informed by thinking about sort of the whole story of multi-way Turing machines and things like that. And it's all, and the question of how does it become useful to humans, I think, is deeply interwoven with questions about sort of the nature of consciousness and what it is that we want to sort of get out of a computation and so on. I think that, well, I kind of got into thinking about this actually as a result of thinking about combinators last month. One of the things that was true historically about combinators, combinators were invented in 1920. NAND, the way of taking, and, or, not in Boolean algebra and reducing everything to a single NAND operation, that was invented kind of around 1900, but became sort of well-known around 1910. And you say, well, NAND, that's just a footnote. Who cares about that? That's just, a detail of how Boolean algebra works. But actually, well, no, people really do care because every computer is just full of NAND gates or NOR gates, which are equivalent. That's how CPU chips work. Because it's easy in metal oxide semiconductor technology to implement a NAND gate as a field effect transistor, you make your computers out of lots and lots of NAND gates. That's the sort of model of computation we're using for computers. And so I had wondered, if history had been different, could combinators, instead of NANDs, have been the basis for computation. And I realized that if molecular computation had been understood in 1920, then it would have been perfectly possible, or conceivably possible, that combinators could have been operating at a molecular level, and we would have just an utterly different view of how computation works. Now, you know, yeah. So I mean that's kind of the a motivation for thinking about the sort of chemical, multi-way chemical computation. It's kind of ironic that those chemical processes might not deeply use quantum mechanics, but the formalism for thinking about this multi-way system is a formalism of quantum mechanics. And so we'd have sort of quantum computation, but it's really classical chemicals in effect. They have some quantum mechanical effects, but that's not the most important thing. It's sort of a classical chemistry, but being thought about in a quantum way through multi-way graphs, and that's leading to the sort of model of computation. Now, you know, another thing we've been working on, although we need to do more work on it, is thinking about what we can understand about sort of the explicit model of measurement and how that relates to what's actually possible in quantum computing. And I think, you know, the irony may be that the formalism of quantum computing gets applied to something that isn't terribly quantum mechanical, but its formalism is quantum mechanical. And so a lot of the mathematical development, it becomes very important, even if there's no magic of quantum mechanics, really. It's a magic of multi-way systems rather than a magic of quantum mechanics. Well, so there are, oh gosh, lots of other, I mean, other things I've been thinking about to do with the application of multi-way systems in things like distributed blockchains and so on. One of the things that I actually probably will write something about soon, the second law of thermodynamics and law of entropy increase the notion of heat. These kinds of things are things that I think I understood back in the 1990s on the basis of computational irreducibility and so on. But it's interesting to see how that interweaves with things about sort of distributed blockchain, where there are a bunch of transactions happening. How do you think about those transactions? How do you think about them as terms of sort of things happening in space-time, where now space is sort of the transaction space of the world, and you think about kind of multi-way graphs, and you think about sort of consistency of transactions and settling ledgers and things like this, settling transactions, creating ledgers, things of that kind. How do you kind of think about those things in terms of what we're thinking about in physics? And we think about kind of event horizons of things that are sort of forks in blockchains and all kinds of things like that. How do we think about those kinds of things? And you know, there are things that I've been certainly wondering about sort of foundational questions in economics, about sort of what is the true source of value in economics, and is it related perhaps to computational irreducibility? Is it something where all this activity is in a sense unwindable? I mean, that's kind of what happens, what one imagines happens in thermodynamics, in quantum mechanics, that to the observer, who is not able to go in and do all the computation to sort of unwind what happened, the behavior that occurred is unwindable. That is, entropy increases. You can't see the egg unbreaking itself, so to speak, because you're not capable of doing the computations that are involved. It's a sort of computational boundedness of the observer through computational irreducibility leads to conclusions. Is that related to the way that one can generate a sort of a coherent notion of value in something like economics? That may be informed by sort of using our kind of physics-like methods to actually make a kind of idealized model of an economic system in a different way than it's been done before. And by the way, not wishing to leave anything out, but also haven't done too much on this recently, but people from our summer school were working on using our models as a way to think about biological evolution. Another area, I mean, what we're basically doing is we're knocking off a bunch of areas where there haven't been successful mathematical style theories. And perhaps the reason is because those areas have kind of stuck in multi-way systems and computational irreducibility, which are two kinds of concepts that have been bubbling around, but they haven't really been crystallized in a form where one can start thinking in terms of them. So let's see, a few other bits and pieces. I mean, I've been thinking a little bit about kind of the physics of alien intelligences. I don't know how to say that better because it sounds like it's the physics of the intelligence. That is, does it have green eye stalks and how do those work and so on. But what I mean by that is more, how would an alien intelligence perceive the universe, perceive physics? What kinds of features of physics as we perceive it now, as we break the universe down in our particular way, are features of our detailed sensory system, and to what extent can we get around that? To what extent would our perception of the universe be different if we were way different sizes, if we had very different kind of branching behavior, if we had different notions of consciousness? What happens if our consciousness is split across an event horizon? How does that all work? What do we perceive in that case? All those kinds of things. And so, why is this interesting? Well, I think it's interesting because it again gives you these ways we believe in our models that this kind of rulial multi-way system that represents the physics of all possible physics is kind of the ultimate model of the universe. And our particular perception of it, which will lead to particular rules and particular conclusions about breaking the universe down into electrons and quarks and all this kind of thing, is a consequence of kind of our way of choosing to describe the universe. And so it's interesting to kind of see what would be kind of a rulial Lorentz transformation, a sort of a transformation to a translation to a different way of describing the universe. What might that look like? What clues can we get about how that might work? It's kind of a pretty humility-inducing thing because it just makes you realize how little we understand. I think that 20th century physics, with its great sort of progress in relativity and quantum mechanics, and to some extent statistical mechanics, that represents a particular slicing of this rulial multi-way system of describing the universe. What are some other slicings? Is there a completely different slicing where we don't think about the universe in terms of particles and space and things like this, but something completely different? How does that work? And is that relevant to, for example, our thinking about very very sort of physics-like things like bulk metamathematics? Is there a way of thinking about sort of this bulk metamathematics that is something like the way an alien intelligence would think about our physical universe? Is it in fact the case that in mathematics, are the mathematicians all aliens, so to speak, thinking about metamathematical space in a way that is somehow incoherently different from the way that we think about physical space? I suspect not. I suspect that it will turn out that actually they're really the same thing, and that they're both reflections of kind of the human way of thinking about things. But that's another piece of this. Now, I might mention in terms of all these analogies of whether it's analogies with multi-way Turing machines. I've been looking at multi-way systems based on numbers, ways of thinking about game trees in terms of multi-way systems, ways of thinking about sort of blockchain transactions in terms of multi-way systems. In one sense, this is applying ideas from our physics project to all these other areas. In another sense, it's taking intuition from these other areas and applying it back to our physics project. But there's another thing as well, which is if we get used to thinking about, doing economic transactions in this multi-way system in a sort of quantum mechanical way, we get to get more intuition. We get to really internalize kind of how these sort of quantum processes work. And it's something, my friend Dick Feynman was fond of saying, nobody really understands quantum mechanics. And I think we are within some kind of distance of actually being able to say we actually are beginning to understand quantum mechanics. And what I mean by that is that it becomes a truly intuitive thing that we can actually sort of wrap our brains around. Now, it doesn't help that probably the wrapping our brains around it means we have to do things like understand how a branching brain perceives a branching universe and so on, and that's difficult stuff. But I think that getting familiarity with, it's just like quantum mechanics, that when you play tic-tac-toe, there can be many different things that happen, but you only care about who wins the game or who loses the game and so on. That and other places where sort of our intuitive interaction, we're used to dealing with things that relate to sort of classical physics and mechanics. We're not used to dealing with things that relate to quantum mechanics. But as we pull the quantum formalism up to being able to talk about these kinds of things that are kind of everyday phenomena, it becomes much more plausible that we can get an actual intuition about things that happen at sort of the quantum level. And that's, I think, to me, making progress in thinking about these things in the fundamental theory of physics, it's it really helps to have intuition like that. I mean, in a sense, one of the things that's allowed us to make progress on our project in general is because we have a source of intuition that really didn't exist before, which is computer experiments. And not only that, technically, computer experiments that involve graphs and laying out graphs and all kinds of things, the whole sort of stack of things that has become possible with the whole Wolfram language story. And I think that that's, in a sense, that's why we're able to make progress now, is because we have that different intuition. I sort of want to re-leverage that idea by getting us even more intuition, by having sort of everydayized the things that come from the sort of quantum formalism. And I think another piece to this is applying this kind of distributed computation, quantum formalism, applying that to thinking about language design. Now, it may be tough, because it may be that there's a fundamental disagreement between the idea of consciousness and the idea of parallel computation. It could be that sort of the notion of a thread of consciousness is deeply interwoven with the notion of a single thread of execution happening. And it may be that we really only by trickery, so to speak, can somehow just manage to handle sort of programming in a reference frame where many things are happening and so on at the same time. I don't know how that's going to play out. It may be that we say, I mean, and then this is again, you know, the world of the language designer is, can you take the things which are computationally possible and make it so that humans can describe what they want to have happen? And so it could be the case that the things we want to describe as having happen are things that are sort of consciousness related and have this sort of single thread of story to them. But I think it will be the case that still in the sort of the best execution of those things, it may be sort of multi-threaded. So as an engineer who's going in and trying to build something that works with that, we potentially have to understand it, to have a way of wrapping our brains around it. Now, you might also argue, and this is perhaps not an unreasonable argument, that one of the big things that comes out of studying the computational universe of possible programs is a new methodology for engineering, where basically you're saying, instead of constructing things step by step, where you can always foresee what's going to happen, just say, here's the constraints on what I want to have happen. Now, go out in the computational universe and find me a system that behaves that way. And possibly what will happen is that we'll be able to say, find me a system that behaves that way. It's doing all these complicated parallel things. I mean, already we have examples of this with finding cellular automata that do all kinds of things, that has all this kind of complicated parallel behavior. It's much worse with multi-way graphs, that much more difficult to understand than cellular automata, that has all these very difficult to understand things, but nevertheless it satisfies the big constraint that we want, that might be a rather non-parallel kind of constraint. But so then that's kind of what's happening inside is all this weird, complicated stuff, and then at the end we get something we want. But you know that's in a sense then that would make it there would be a more difficulty in opening the black box and understanding what's going on inside than perhaps we'd even ever imagined before. And we think in quantum computing and in quantum cryptography and things about, you know, if you perturb the box, all is lost. All these quantum threads will all become inconsistent and so on. I think that perhaps there are other senses in which kind of to open the box and look inside, there will be some sort of ideas from computational irreducibility about no user serviceable parts inside the quantum box, so to speak. And that's a sort of feature of the structure of quantum mechanics and quantum measurement, but it might also be a consequence of there are no user serviceable parts for a computationally bounded user, so to speak. That the user can't go in and monkey with things because the user will always break it because of computational irreducibility, because the user can't figure out enough what's going on to not break it. By the way, the thing I did a couple of months ago of looking at faster than light travel in our models and observing that if you can hack the structure of space well enough, then most likely you can go faster than light. By which I mean that there is space has sort of some aggregate behavior. There's a sort of aggregate knitting together of space that happens through all the events that are happening in space. But if you can pick the exact right sequence of sort of pieces of space to go through, you can potentially sort of go faster than the general sort of light cone of expansion of effects. Your effect, the effect of you, the sort of trajectory that you follow can be one that exceeds the rate of the light cone of generic effects. But that's, again, something that relies on sort of breaking computational irreducibility, so to speak, being sort of super computational, being able to do that irreducible computation. Well, let's see. I'm probably forgetting some things, but a lot of interesting stuff going on with the project right now. I would say that I would like to say that one of the things that's really nice is sort of increasing interest and enthusiasm about the project among physicists, mathematical physicists, computer science people. By the way, we'll probably have some really interesting things to say in the not too distant future about computational complexity theory, which is also deeply related to this whole story of multi-way graphs. The multi-way Turing machine is a story of non-deterministic computation, and kind of one of the big, one of the big questions in computational complexity theory is the P versus NP question. Are there fundamentally more computations that can be done non-deterministically than can be done deterministically? Is the in a given amount of time? And we can kind of see that is ultimately a geometrical question in rulial Turing machine space. I haven't answered the question, but we can see at least how to define the question, how to set the question up in a very different context than the one it's been set up in before, and a context in which we can start to use sort of ideas from physics to characterize what's going on. All right, so that's a little bit on what's happening, and we've got a bunch of questions here and comments. Let me see if I can scroll up to the top and start addressing some of these. So, first question from Ettore. Hold on 1 second here. Okay, since Turing-complete systems can emulate other systems, isn't it in a sense true that any Turing-complete system can represent our universe? Thus, many rules might well represent what happens. Can you describe the complexity of translating between different computational models that represent the same thing? Right, so this is exactly the story of rulial multi-way systems. You're exactly right, that the story in the end that there is only one ultimate model of the universe is the story of the fact that the universe is computational, and that any old Turing machine can in principle represent the universe. The issue is to go from our kind of sensory apparatus and our way of describing the universe to figure out what those effective Turing machine rules are and sort of what we have to run to get a model for the universe in terms of that Turing machine rather than in terms of some other computational system. And the whole point is that this description in terms of spatial hypergraphs and all these kinds of things is something which seems to be a bridge between our human ability to understand things, our ability of our computers to operate on things, and the way the universe actually works. It's kind of this three-way conversion, this three-way translation. This question about the difficulty of translation, this is a question about things like you can imagine a different reference frame in rulial space corresponds to a different way of sort of the way of exploring that's a different way of kind of exploring rulial space through time. So as time goes on, things happen, but you can be using some of the time that passes to do translation, or you can use the time that passes to actually evolve the universe in your particular model. So you can be kind of, as you make a transformation between reference frames, that's asking sort of what that Lorentz transformation effectively is asking for the sort of effort of translation. And so time dilation in rulial space is the story of translation slowdown, so to speak, of, it was really supposed to be, we're describing it in terms of a Turing machine. There's effectively time dilation relative to the description in terms of something else. And so characterizing that time dilation, very interesting question. I wrote a little bit about this in the piece that I wrote about rulial Turing machines. There's this parameter, I think we're calling it rho, that is the analog of the speed of light in rulial space. So the speed of light tells you if you have an event that happens and it's going to affect other events, it tells you the translation between, let's say, some amount of time elapsed. You say 1 unit of time elapsed. How much space can those events that were both affected be apart? And the answer is, if the time that's elapsed is t, those things can be essentially c times t distance apart, where c is the speed of light. We also think that in multi-way graphs, the brachial distance that things can be apart is, our zeta times times t, where zeta is the maximum entanglement speed. The analog of speed of light is the maximum speed that you can go, is the separation, the unit separation in brachial space associated with the single elementary time is zeta times the elementary time. And in rulial space, same story again. In rulial space, again, there's a certain sort of translation, a maximum translation speed so essentially what it's saying is, if you say, I really want to describe the universe in terms of this thing, it could be that it takes you longer to do the translation than it sort of takes the universe to evolve that next step. So in a sense, that's a frame you can't get to. You can't make a transformation into that frame. And so there's this maximum speed, and there's even a fun question of what units is that maximum speed, that rho, that maximum speed in rulial space, what units is that in? And I realized that the right units it's basically in units of, it can be in units of Wolfram language tokens per second. So it's in units of computational stuff processed per second. It's in units of sort of amount of computational input per second. Whereas the maximum entanglement speed is probably best represented as essentially an energy or a speed of light per second. And maybe in our rough estimate, it might be 100,000 solar masses per second. And that's, by the way, relates to the whole phenomenology of our models. And is that observable in quantum computing experiments? Is it observable in gravitational wave-like detectors? How might that be observable? Okay, question from Techrific. Wishlist for this update. Succinct overview of general and specific findings so far, challenges at the moment, development of technologies specific to this project. Okay, well, I think I tried to cover some of those things. Challenge at the moment, just see how widely applicable the things we're doing are to all these other areas and sort of intermesh the intuitions of these areas. Also, this sort of discrete differential geometry story and the build out for that. I would say we're doing pretty well on understanding quantum mechanics in these models. Getting to quantum field theory is another thing. I would say that we have now pretty decent understanding of things like the classical physics of event horizons, associate that with brachial space and be able to actually start observing things along the lines of sort of the Hawking radiation, holographic principles, all these kinds of things. We're kind of bubbling at the edge of these kinds of things. Another question is making more connections with existing models. For example, string theory. I'm really fairly certain that, bizarre though this pun means, is the continuum limit of the string rewrite analogs of our hypergraph rewritings is probably string field theory. And make that precise, figure out what that means, and then import, if that turns out to be correct, import ideas from string theory to our models. So making all these kinds of connections. Similarly to spin foams, spin networks, we're getting fairly close to understanding how that works, but we're not quite there yet. Technologies specific to this project, well, we've been putting a lot of new things in the function repository that are for this project. I would say that the big thing that we are planning is multi-way systems. It's clear multi-way systems are of very global importance for lots and lots of kinds of things. And we're trying to sort of package them in such a way that they can be used for general programming. And so, for example, logic programming is kind of a story of pathfinding in multi-way systems. That's been a methodology of programming. It's used sometimes for constraint satisfaction and so on. I think it could be more mainstream. I think the big challenge is to have an understanding of distributed computing that comes from our emerging understanding of quantum mechanics. And that I consider to be a major challenge for upcoming time is how do we ingest these distributed computing ideas into our language? And how do we do things which make real these things like the programming in a particular reference frame idea and so on? How do we what are the primitives? What are the basic sort of functional programming primitives of this distributed way of thinking about the world? Multi-way system is definitely one of these. What other kinds of things like that are there? How does that enmesh with our whole theorem-proving technology? How do all these things fit together? Well, here's one that I've been trying to solve for 40 years, is causal relationships in programs. So how do you find a trace of the causal relationships in the operation of a program? How do you think about not only the execution of a program, but also its internal causal dependencies? This is sort of important in getting, execution traces of programs, in trying to understand more globally how programs work, and in being able to do sort of things in parallel. Okay, let's try and get through some more of these. So Jay's son asks the question, Wolfram math to English translator. Boy, English is not a great language for representing the computational world. That's why I've spent 40 years building computational language to represent the computational world, so to speak. I think that it's that's kind of a story of that kind of thing. So yeah, I think what we're aiming for is a computational language. I think we're kind of aiming in a different direction. Rather than saying, okay, translate everything we're doing into English, which I don't think is going to work. It's like you try and write the contract of the universe in English, you write it in sort of legalese, and it's going to be absolutely incomprehensible. So then the alternative thing to do is to say, say, well, let's write it in computational language, but then it's like, oh, but the humans don't understand that. Well, that's what we have to fix, is have the humans understand computational language better. That's been the story of kind of the advance of Wolfram language and its use in more and more different places, is provide computational language literacy for humans. And that way, what you might now say, oh, I don't understand it, it's not in English. I don't understand it, it's, it is in English, it's not in mathematical notation. I understand it better in mathematical notation. So, some of us understand things better now in computational language than we would in plain English. And that's sort of the direction to go in. And I think, one of the things about our project, okay, so here's a question about our project. If we hadn't done this project now, when would it have been done? And this is something that I think is kind of scary to think about, because, I've been thinking about this project in pretty much the terms that we've ended up doing it for 30 years. And, beginnings of it, at least at that time. I didn't know how well things were going to work. It was worked unbelievably much better than I expected. But the rough direction, the rough roadmap, I've known for a long time. And I even told, millions of people about it nearly 20 years ago. And it didn't happen. And, but there are other developments in mathematical physics that are sort of vaguely going in this direction. But they're not, what we're doing is like jump to the end. We can see this is a machine code. Now you can see how that mathematical physics kind of connects into that. How long would it take? I don't know. 50 years, 100 years? I don't know. Long time. And, it's very sort of satisfying, gratifying to feel that one's actually managed to sort of accelerate the future by a significant number of decades. It's not super surprising if one's been working on it for a few decades that one has reached sort of a platform where one can accelerate things by some number of decades. But the challenge of computational language is it is an absolutely inexorable thing that will be the way that things are represented. That will be the way that people choose to represent things eventually. Just like I realized, 30 years ago now, that modeling things in computational terms, just making computational kind of program-based models instead of kind of mathematical models, was absolutely inevitable. But it's taken a while, a few decades, for that to become something that is widely understood and widely used. I mean, it's remarkable that it's only been a few decades, because there was 300 years before it when it was just mathematical equations all the way down, so to speak. But this sort of process of computational language being a thing that is widely understood, sort of widespread computational language literacy, it's The big challenge is how much can we accelerate the future? Left to its own devices, that future might take 100 years to happen. But to what extent is it possible to accelerate that future? And it's a lot of effort, and it's an effort that is beyond the effort of actually building what's possible. It's also an effort of kind of educating the world, and it's an effort that we hope other people can increasingly help with, and certainly many have been. And I think that in a sense, what our physics project does is to say, oh, this computational view of the world, this view of thinking about things in terms of computation, it's not something which is sort of optional. And not something, well, you can do that, but you can also think about things another way. We really know from this physics project that the universe is basically computational all the way down. Now, there may be many different slices of how we think about that computation. Are we using general relativity and quantum mechanics, or are we using this bizarre, incoherent notion that our sort of friendly aliens might use to describe the universe? That's a different issue. Well, let's see. Question from Ido. Can it be considered that the universe calculation will be reduced to a trivial state and from there just start from an initial condition, reminding people of Roger Penrose's, I think there's a cyclic universe idea. Initial conditions are very interconvertible with rules. In this kind of rulial multi-way system story, there really isn't a difference between initial conditions and rules. I mean, you can always say, oh, and there's an additional rule that says from nothing make this initial condition. So there's not really a close distinction between initial conditions and rules. But I think in a particular kind of rulial frame, in a particular way of describing things, yes, there will be initial conditions, there will be rules. I think that the thing that is likely to be the case is that the initial condition will be very simple. And why do I say that? I don't think I have any good reason to say that, actually. But the one thing I can say is that we won't notice if it isn't, because that initial condition is so immediately covered up by layers of computational irreducibility that it will just look like this complicated thing, even though it might have a simple origin. Even though the rule 30 starts from just the one black cell, it's quickly made this pattern that seems very complicated. And I think the same thing with the universe. In a sense, we might say, well, probably it does. Maybe it does start from a simple initial condition. Maybe it doesn't. It doesn't really matter, because the things that we are actually capable of observing with our bounded sort of computational observer capabilities are things which don't depend on that detail at all. So that's my guess. In the end, it won't matter what the initial condition is with respect to the things that we measure about the universe. It will matter if we were able to go in and look right down at the machine code, so to speak, and see exactly what's happening. Then it would matter, but it won't matter at kind of the level that we're able to look at things. There's a question from Abhishek about our views on the universe being a simulation. I think that's sort of a somewhat philosophically doomed concept. I think that what is a simulation? A simulation, when people say that, they mean we're inside a video game. The aliens are playing a video game. We're part of the video game. That sort of implies that there is something sort of outside the universe. It's a very, very kind of traditional theological kind of view. It's kind of the, it's a God not in the clouds, but out at the video game console, so to speak, who is somehow intentionally creating the universe. If the universe just operates according to certain rules and there is no choice about what goes on, then yes, you can say, well, there is a video game creator, and that video game creator set up the video game, but then the running of the video game is really quite independent of the video. The God isn't pressing the buttons. It's just, there's just a thing that's running. So then you say, well, but the God started the universe. At least they set it up, you might say. Well, that's the story of this whole rulial multi-way system thing. Actually, it didn't have anything to do, because any universe would have been as good as any other. The perception of the particular rules being used, all possible rules are being used. It is merely our perception as observers in this universe where we choose to describe it in a certain way. So in a sense, the simulation is there is nothing for the simulator to do. There is no, it is something where there isn't a, it's kind of like there is no notion of sort of a controlled simulation of the universe. It is just, the only thing about the universe is that it is computational. It's actually this principle of computational equivalence of mine ultimately ends up being the only ultimate law about the universe, is that fact. Now, you might say, well, what about maybe there's a simulator, a God figure who's sort of a hypercomputer that's kind of outside our universe. Well, the problem with that is there's sort of forced to be an event horizon between the sort of hypercomputational and the merely computational that makes it impossible for there to be causal connections between these two things. So it's kind of like yep, I got this video game, but I have no control over it, and it's this thing that I can't communicate with. So that makes it pretty uninteresting for a simulator, so to speak. So I think it's in the end, it's sort of a mixture of sort of understanding the physics and in a sense, perhaps the philosophy of it. I could expand a little bit more on that and the sort of a lack of a notion of independent notion of purpose for things embedded within a system based on rules and so on. I just don't think that, I don't think that's a useful thing to think about. Now, an interesting question, given that I'm talking about these different ways of thinking about modeling the universe. Okay, so here's a fair question to ask is, we have this model that involves relativity and quantum mechanics and laws of physics and so on and so on and so on. But maybe there's a different model. Maybe the different model is the simulation model where we just say there's a godlike figure that's puppeting the whole universe. Is that a reasonable model for the universe? Well, maybe it's no less reasonable than a model where we have all these rules and we know what's going on and we can work out this and that. We could equally well say, well, the puppeteer has certain rules associated with them that turn out to give us the universe. So in some sense, in some sense we can think of it as not as well developed as the laws of physics, but we can think of it as an alternative way of modeling what happens in the universe, although it doesn't have the benefit of all the things that come from our sort of detailed sensory knowledge of the universe and our detailed development of physics. I actually hadn't thought about it quite that way before, and perhaps there's more to think about along those lines. I mean, I think the big challenge there, somebody asked about challenges. Okay, so here's a challenge. We might have some understanding of the why this universe and not another question, in the sense that the universe as we perceive it is a reflection of our ability, our way of perceiving things. But there's a different kind of twist on this, which is, why does the universe exist at all? Why is there something rather than nothing? To say that there is a formal system which can be the universe is not to explain why the universe in actuality exists. And so one of the things we've been wondering about is whether it's possible to make any statement about why the universe exists. In a sense, one question is, can we take the statement, the universe exists, and compile that statement into something which is essentially runnable inside the universe? This is kind of like what Gödel's theorem tries to do. It tries to take, well, Gödel's second incompleteness theorem, for example, tries to take the statement, arithmetic is consistent, and compile that statement into something that can be run inside arithmetic. And then that leads to inconsistencies, and so you can say that statement is undecidable. So the thing would be to take the statement, the universe exists, compile it into something where you can say, okay, if the universe exists, then this particular arrangement of masses and black holes and this is and that's and the other will flash a big sign that says 42 or something at the end of it. That you can compile the statement, the universe exists, into something executable within the universe. And from that, you can derive an inconsistency, which would then imply probably that for observers within our universe, it is forever undeterminable, undecidable, well, why the universe exists, or in a sense, even whether the universe exists, that is an independent statement. The existence of the universe will be a statement independent from anything accessible from us within the universe. We don't know if that's really right yet, but that's a possibility it's in some sense an unsatisfactory, in some sense a satisfactory resolution of the question of why does the universe exist, is we'll never know, and we can never know. Okay. So question from Walter White. What does it mean for our project if quantum computers are going to work? Our project and our models basically reproduce quantum mechanics. So they reproduce whatever should happen in a quantum computer. A better question, I think, perhaps is, what does our model say about how quantum computers can work? Because our model, in ordinary quantum mechanics, as developed in the 1920s, there is a theory of how quantum states arise, how superpositions work, all these kinds of things. But then there's a mysterious piece. It's like, and then you do a quantum measurement. Boom, there's a result. There's something definite that us humans can say, this definite thing happened. That is viewed as essentially an atomic act, an indivisible act in the standard formalism of quantum mechanics. In our models, measurement, we understand it. Well, there's more to understand about its mechanics, but measurement is a thing that actually has mechanics in our models. There is actually a model of measurement. And so Jonathan has his particular interpretation in terms of these completions. There may be some other ways of thinking about it. I suspect they're all ultimately equivalent, although they may be very different in terms of our actual way of thinking about them. But they're probably mathematically equivalent. But in any case, this gives us a microscopic model of measurement. And so it allows us to answer questions like, given that the quantum computer could do all these things in parallel, how much effort would it take to make the measurement to find out what happened? And so I think that's going to really tell us a bunch of things about what is theoretically possible in quantum computers. My guess is that we will say at the end of it, we'll notice some global effects associated with the mechanics of measurement, and we'll eventually say, aha, this decoherence that was observed in a bunch of quantum computer experiments might very well be a reflection of this generic phenomenon that we're seeing as we look at the mechanics underneath measurement. In fact, it even occurs to me that perhaps there are things that we could think about in terms of already known things where people say, this is a typical irony of the history of science, okay? The thing that people think is a nuisance in their experiments turns out to be the main effect. So, for example, when people in the early 1960s were trying to do satellite communications, and they were like, "Oh, drat! There's a flaw to the microwave noise level, and it's a 2.7 Kelvin flaw, and we just can't get lower noise from our satellite transmissions than the 2.7 Kelvin flaw." And then it was realized that's actually the cosmic microwave background. That's a real effect. That is a very interesting piece of physics about our universe. And I wouldn't be surprised if there weren't effects, phenomena in quantum computing that have been observed in experiments on quantum computing where people say, drat, this decoherence is happening at this rate in this quantum computer, this thing is going wrong, this, et cetera, et cetera, et cetera. And they just think of that as a drat type thing, but actually it will turn out that that's a piece of physics, and that there's actually a general model that can be made for some of those kinds of things. And perhaps our models can help inform what to look for and how to think about that. As I think about that, I think that's a very reasonable thing to ask, is kind of inventory what's actually been observed. See, one thing that happens in experiments is the following, that people know what they're looking for, and they look for it. And if they're good experimentalists, if they find it, they report they found it. If they didn't find it, they report they didn't find it. If they're, that's the challenge of experimental science, is to sort of accurately, independent of what you think you're looking for, report what's going on. Much more difficult is to look for things you weren't looking for, is to see things you weren't looking for. And much more, there's a great tendency to just sort of ignore the things you're not looking for. I know in fluid mechanics, a phenomenon that I predicted a long time ago of repeatable random flows. That's been observed in a bunch of experiments. I don't think anybody's yet written a paper about it, because people think that's so weird that nobody could think my experiment would be correct if I saw that. It's so unexpected that it's hard to convince yourself that you really did the experiment correctly. And so it could very well be that sitting right under our noses are sort of some new fundamental facts about quantum measurement, which are just really could be found by a meta study of things that have gone wrong in quantum computing and gone right in quantum computing actual actually doing quantum computing, but nobody reported on that. They just said, oh, well, here's what we achieved. Well, there was also a bunch of problems we ran into, but we didn't report on those because the only thing we're concentrating on is what we achieved. So I suspect there might be something there, and that might actually be something closely related to our models. And I hadn't really thought about that properly before. And so thank you for that question. Okay, another question here from Crunchy. How much time is there between the start of our universe's rule and the inflation moment in the Big Bang? Well, we don't know the answer to that yet. Okay, the notion of time is a complicated thing. So in our models, time is actually something much more definite in some ways than it is in traditional physics. In traditional physics, it's just a coordinate. You can pick that coordinate of time, you can pick coordinates of space. They're sort of interchangeable in some ways. In our models, time is this inexorable, irreducible computational process that's going on. That's what leads to the progress of time, and it's a non-trivial fact that that's equivalent to various aspects of space. It's a consequence of this phenomenon, this thing we call causal invariance. And so this question the question is, we've got the start of the universe, and we've got computations going on, and then we've got and that defines a notion of time. And then we've got the way that space potentially inflates. So inflation probably in our models is probably associated with exponential growth of this spatial hypergraph. That's if there is something like inflation, and there might not be, because in our models, it might just be that the universe starts infinite dimensional and gradually cools down. We don't yet know enough of the cosmological phenomenology to be able to say that we need inflation in our models, that there even is a thing like that. There'd be a thing that was a little bit like that, because it would be like the universe is infinite dimensional, and so it has all this connectivity, and that's sort of achieving some of the same things that inflation achieves. So, but it isn't strictly inflation in that sense. At least I don't think it is. I think there might be a way in which you can transform the coordinate system to make it look like, I bet there is actually. Well, it's a little bit complicated, because ordinary inflation is in 3+1 dimensional space, and it's merely an inflation of the spatial metric. Whereas what we're talking about here is inflation, and is dimensional inflation as well as spatial inflation. And exactly what the correspondence between those two things is, I'm not sure. We should let Jonathan say things here. I bet Jonathan knows the answer to that. So maybe Jonathan could jump in if he has a comment on that particular thing, and then we can go on with some of these questions. And then I kind of think Jonathan probably has all kinds of things to say, and has probably been very frustrated that I've been saying the wrong things.
That's quite all right. But on the connections between varying dimensional cosmologies and inflation, there is at least a proof sketch in my first relativity paper that I wrote on the project that shows, so first of all, that if you have an infinite dimensional space, or effectively infinite dimensional space, a Riemannian manifold that converges down to something finite dimensional, then what you end up with is a conformal structure of space-time that matches that in which you have essentially a varying speed of light. And the reason for that is quite easy to see, because what it means for a hypergraph to correspond to a very high dimensional Riemannian manifold is that it has very, very high connection density. So what that means is you can basically propagate information from one side of the hypergraph to the other very quickly. And as it cools to something finite dimensional, it's becoming progressively more sparsely connected. And so it's as though the effective speed of light is undergoing some sort of phase transition. So you can make a connection, an immediate connection between these varying dimensional cosmologies and what are called variable speed of light, VSL cosmologies. In particular, I was able to show how in one model of this phase transition, you could recover what's called the Petit-Albrecht VSL model. And what's significant about that is that the consequences for the conformal structure of spacetime on a large scale from a VSL model of cosmology are provably equivalent to that of a standard slow roll inflationary cosmology. So they provide equally valid solutions to the horizon and flatness problems in lambda CDM. Which means that, so if this is sort of what happened in our universe as modeled by a hypergraph, it would be essentially observationally indistinguishable from a slow roll model of cosmology, except for the fact that there would presumably be signatures of the dimension decay, which would not exist in inflation. And if we want to sort of be able to test this observationally, those signatures would essentially be the things we need to look out for. By the way, just on this particular question about the amount of time between between sort of the start of the universe and the start of basically, the sort of hot Big Bang model. So Stephen, you mentioned there's, there are some subtleties about exactly what time refers to, and that, that's absolutely correct. I mean, so our model gives us one very concrete notion of time, which is just rule applications. But, and so in effect, you could, time-like separation in the causal graph is just a measure of causal edge distance, which is a measure of, number of rule applications between two distinct events. But there is that, that's not the notion of time that's actually being, perceived by observers. The notion of what a relativistic observer is, just like a quantum mechanical observer, is essentially a definition of a time function over the causal graph. So when you define a foliation of the causal graph as a relativistic observer, what you're basically doing is defining a time function over that causal graph whose level surfaces are the hypersurfaces in that in that foliation. And that's the notion of time that you as a relativistic observer actually perceive. So there's a kind of underlying computational time, and then there's a kind of imposed physical time. In a similar way, in ordinary cosmology, you have the notion of proper time, which is kind of which is the physically measurable thing, and you have this notion of conformal time, which is where your time parameter is basically defined in terms of an integral over the scale factor a of t of the universe over dt. And conformal time is the thing that's kind of relevant for analyzing the causal structure of these models of cosmology. And what happens in the inflationary model is that in the ordinary hot Big Bang model, in the lambda CDM model, the initial singularity, the start of the universe, and the start of the lambda CDM expansion happen at the same time. They both happen at time t equals 0. But in inflation, what you do is you add in this exponential growth to the a of t term, so that what happens is that the initial singularity gets pushed back to negative infinite conformal time, whilst the transition to the hot Big Bang model still occurs at time t equals 0. And so what that's telling us is that if there is a kind of inflationary phase transition that happens in our models, then there will be essentially an arbitrarily large number of causal edges separating the initial singularity from the start of the hot Big Bang model. And when I say arbitrarily large, what that basically means is the number of causal edges is in some way a function of the underlying discretization scale, because in the continuum limit, that separation should be infinite. Yeah, I mean, something should investigate in
well, it's interesting. I mean, one point to make is in terms of these different notions of time, for a photon, no time has passed since the photon last scattered, when it created a photon in the cosmic microwave background. As far as it's concerned, the universe just started. Its conformal time is, no time has elapsed for it. And that's a version of kind of this observer time being different from some underlying, mechanics of the system. But yeah, there's so many things to investigate here. Nobody at our winter school investigated inflationary cosmology, did they? That would have been another good topic.
No, there wasn't anyone with a relevant background, unfortunately. I did have one comment to make on the at least on the initial conditions question. So you were saying that you didn't feel as though you had a kind of particularly knockdown argument for why the initial condition has to be simple, except for this kind of, masked by computational irreducibility thing. I think we do essentially have an argument for that, and it actually relates to the very first question that Ettore asked about. So, in a sense, if the universe is Turing-complete, is Turing-computable, then surely, we already know the fundamental theory of physics, and it's just that the universe is a Turing machine. And although that's kind of trivially true, what's interesting is how you set up that computation and how you kind of decode the results of it and make connections with things we actually know about in mathematical physics. So the point is that if you allow the initial condition for, in one of our models to be arbitrarily, so we know that our models are capable of universal computation. So if we allow the initial conditions to be kind of arbitrarily complicated, then we could set them up to basically simulate any theory of physics that kind of, that is in principle computable. So in a sense, if we allow, arbitrarily complex initial conditions, the model ceases to have any kind of predictive power. So the only sense in which we can say that our model is actually a model of physics that has genuine predictive power is if we impose a constraint that says the initial condition basically has to be trivial. Because if you allow for kind of non-trivial computation in setting up the details of the initial condition, the model has lost any predictive power that it might otherwise have had. I may not have explained that particularly
well. Well, I think that's you're also explaining a version of the simulation argument. The simulation argument is the God simulator is feeding in initial conditions rather than is setting up initial conditions. But that's as you say, that's also something where you could build those initial conditions from a computation. And it's I mean it's a good point that.
Same challenge you get when proving universality of a system, right? Is that it's really quite complicated because you have to set up the initial conditions and you also have to decode the result. And one of the key problems you have to solve is can you prove that the computation you're doing to set up the initial conditions and decode the results is not itself performing non-trivial, is not itself non-trivial. And basically we have to impose the same restriction here, which I think it ensures that our initial conditions have to be in some sense trivial.
Well, you're claiming that you can't if you put all the physics in the initial conditions, then the game is over, so to speak. And right. So it's not a useful game if you put all the physics into the initial conditions.
Exactly. Just like if you did all the computation on the initial tape of a Turing machine, that's no good for proving universality of that Turing machine.
Right. No, that's a good argument, actually. That's a better one than we've had before. Yeah. Well, let's see. Let's go on with a few of these more of these questions here. And okay, there's a question from Ed Polanski. Like us to elaborate a little bit on the ideas of brachial space and how it relates to ADS-CFT and the possibility of using the same to send information. Well, now that Jonathan has started saying things, Jonathan, do you want to talk about ADS-CFT?
I don't think we have a huge amount more to say about this. I mean, there have been some preliminary investigations, some that were done at the Winter School, but I mean, I think certainly you, Stephen, on previous live streams have described the basic idea of how we think the ADS-CFT correspondence works. So right.
Well, I mean, just to give people some sense, I mean, there's in the multi-way graph, there is when you look at events that happen, update events that happen. There are three forms of separation of update events. Time-like separation, one update event leads in progressively in time to another one. Space-like separation, one can think of those update events as happening at the same time at different places in space. And branch-like separation, one can think of those events as happening on different branches at the same time, and the issue is we can make a causal graph that connects all these, that has edges that are both space-like edges and branch-like edges. And the general belief is that the ADS-CFT correspondence is a story of the knitting together of space-like and branch-like edges in this multi-way causal graph. And that, in a sense, the ADS part of it is the kind of space-like projection, and the CFT part of it is the branch-like projection in this multi-way causal graph. Now, there's some things like ER equals EPR, which I think Jonathan has thought about a bunch recently, which are kind of features of the whole ADS-CFT story. Do you want to say something about? I think we're hoping. I'm hoping that your simulations are going to show an ER equals EPR real soon now.
Right. Well, I mean, we already have some initial sort of numerical validation of the ER equals EPR conjecture in the context of these models. So as Stephen says, our basic sort of setup for thinking about holographic duality, ADS-CFT correspondence is that when you take a multi-way causal graph, you can project it into space-time, you can project it into branch time, and that there's some kind of fundamental duality between those two different geometries. So the ER equals EPR conjecture is an idea that comes out of conventional thinking in sort of about the holographic principle in modern physics, where the basic idea is it's connecting ER, Einstein-Rosen bridges, which are these particular topological solutions of the Einstein field equations, basically wormhole solutions, where you kind of have, like, if you imagine sort of stitching together two Schwarzschild solutions with a little neck in between, you get the Einstein-Rosen solution, and what's called the Einstein-Podolsky-Rosen effect, otherwise known as quantum entanglement. And the basic conjecture is you're saying, if you think of ADS-CFT or the holographic principle as being some statement that the entanglement geometry that you get from, say, a conformal field theory and the actual space-time geometry that you get in relativity should somehow be related, the ER equals EPR conjecture is a very concrete instance of a sense in which they might be related. So the idea is, if you think about one of these wormhole solutions as literally being a pair of black holes that are sort of entangled, then there should exist some kind of relationship between the classical geometry, in other words, something like cross-sectional area or the length of the neck that separates the two black holes, and the entanglement entropy that's associated with the two actual black holes as they're entangled, as computed using something like the Fubini-Studi metric, or the Fisher information metric, or the Burroughs metric, or something like that. So there are a bunch of kind of quantitative conjectures that have been made about how those two things might be related. One thing I realized a while ago was that we should be able to test this explicitly in the context of our models, because we now have, thanks to these, thanks to both the numerical relativity stuff and the sprinkling stuff that Stephen mentioned earlier on in the live stream, we can construct explicit examples of the Einstein-Rosen metric, and then we can evolve them as we can evolve those metrics as multi-way systems. And we can actually see what, essentially what the entanglement entropies are, because, in the context of our models, entanglement entropies are given essentially by branch-like separations. So we can construct the metric with a particular, classical geometry, and then we can look at the associated branch-like separations that would exist in the multi-way evolution, and we can just compare numerically how, those two quantities. And actually, if I hang on, maybe I can show an example in, yes, okay, in this notebook. So if I just quickly share and show, sorry, this thing here. So here are examples of these Einstein-Rosen bridges. So these are causal graphs that we've explicitly constructed so as to be able to, so that in the continuum limit, they will satisfy the continuum Einstein-Rosen geometry. And you'll see that I've configured them so that they have varying neck lengths, bridge lengths, and varying cross-sectional areas of the neck. And what I've done up here is plot, okay, so in orange is the theoretical prediction of the relationship between the cross-sectional area of the neck, which is on the x-axis here, and the entanglement entropy that's associated with the separation between the two between the two Schwarzschild metrics on either end. And so that relationship is shown in orange. And then in blue here, you can see the numerically computed relationship between those quantities in the context of our models. You'll see there's quite a lot of noise because of the fact that these are intrinsically sort of randomly generated metrics. These metrics are constructed by basically doing uniform Poisson sampling over a Lorentzian manifold. But if we took limits of arbitrarily large numbers of samples, then the standard deviation here would go dramatically down. But you can definitely see that there is a pretty good correspondence between the theoretical prediction of the ER equals EPR conjecture and the actual relationship between the space-time geometry and the branch time geometry that we compute from our models. So the hope is that we'll be able to validate a few more of these kind of more quantitative conjectures that come out of the holographic principle in ADS-CFT correspondence, and that will help us kind of make concrete this general idea that there is a duality between branch time geometry and space-time geometry. Now, we're sort of limited in a sense by how effectively we can do that because we still don't really have a complete sort of coordinatization theorem for branchial space. We understand coordinatization of physical space much better than we understand coordinatization of branchial space. So in some sense, we're limited by that restriction. But something like the ER equals EPR conjecture is nice because it's a result that we can derive purely, essentially looking only at the combinatorial geometry without having to care about how it actually gets coordinatized and embedded. So we're hoping to be able to investigate a few more of those kinds of results to make more tangible connections with things like ADS-CFT in the near future.
Although you don't need some coordinatization of branchial space to get your branchial distance there, don't you?
Fortunately not. I mean, for the same reason that if we want to know geodesic distances in the hypergraph, we don't need to embed the hypergraph in anything. We can just measure the combinatorial.
I see. Okay, but that's the multi-way. I see. That's the graph distance there.
Exactly, nice. Yeah. But there are more refined conjectures in the context of ADS-CFT that genuinely would require a coordinatization, and which for that reason we can't yet investigate until we understand better how that works.
Right. I mean, I think I forgot to mention the whole coordinatization of branchial space. That's another upcoming big challenge, and I think it's again something where these analog models of things like Turing machines, systems based on numbers, all these kinds of things, help us to sort of work towards what is the right coordinatization of branchial space. Let's see other questions here. A question from John: what happens to the dimensions of space on sub-Planck sizes? Well, in our models, the elementary length, the actual distance in space corresponding to sort of neighboring elements of the hypergraph is actually considerably smaller than the Planck length. Planck length is 10 to the minus 39 meters. Is that right? 10 to the minus 43 seconds. no, one of those is 10 to the minus 35 meters, and 10 to the minus 43 seconds of time. That's our elementary length is more likely something like 10 to the minus 100 meters. So there's already a lot of action between the Planck scale and the ultimate elementary length in the universe in our models. And I think the dimension of space is an aggregate phenomenon. It's like asking, what's the flow rate of a fluid, and you're looking down at the scale of individual molecules. The individual molecules are running around at the speed of sound or something, but nevertheless, the overall flow rate of the fluid is the aggregate average motion of the molecules, and that's something quite different from what it is at the very smallest scale. So there isn't really a notion of dimension on a sufficiently small scale. Dimension is an emergent property of a large-scale system. And it's a perfectly reasonable question whether there could be lumps of different dimensional, as we go down, as we sort of zoom down to smaller and smaller scales, could there be could there be sort of localized lumps of higher dimensional space that we don't notice on a large scale, but on a small scale, we'd see these lumps of higher dimensional space? Well, one possibility is those are particles. One possibility is that's actually how things like electrons work. We don't know yet. It's also quite possible that they work in a way that's a bit like black holes, which is the same kind of statement as the statement that there's sort of a higher dimensional lump. It's all related to the presence of event horizons and all kinds of things like that. Let's see. Talking about meta-mathematical conclusions coming out of the work, let me not go in too much more detail here about that, because I think that's going to get us the real challenge there is, what is bulk meta-mathematics? We think of mathematics as there are 3 million theorems in the literature of mathematics. What's the infinite time limit of mathematics? What is the continuum limit? What does it look like? What does this sort of space of all possible theorems look like? And to what extent can we identify features of that space? What would a black hole in meta-mathematical space look like? That's presumably a decidable thing. It's a thing where all the GD6 correspond to shortest proofs of things, where in a sense mathematicians aspire perhaps to follow GD6 in meta-mathematical space. They aspire to find shortest proofs. They aspire to find the shortest way to get from here to there. They don't necessarily succeed, but they aspire to follow GD6. If the GD6 are, if there's a singularity, then the GD6 end, in a sense, then sort of all theorems are finitely provable, so to speak. That's what happens in a decidable theory. So in a sense, that's sort of a notion of black holes. You can start thinking about sort of what are the notion of event horizons, other kinds of phenomena from general relativity, and what's sort of the analog of the Einstein equations, what's the analog of energy in meta-mathematical space? Is it something about sort of an accumulation of lemmas in mathematical space? How does that all work? What's the analog of reference frames? Is it related to models in mathematics? These are all things that we're sort of thinking about. Let's see, there's questions about, I think we're unfortunately running out of time here. But let me just try and rush through a few of these. Connections to the monster group, we don't know yet. Although there are some really fun things. There's the discrete approximations. I mean, I could show you something that came out of our very, very, very super quickly here, just in the theme of this kind of thing. These are just some projects that were done at our winter school. This is a discretization of non-abelian gauge theory. This is an approximation to the S7, to the 7-sphere discrete approximation, showing the way that this decomposes into fiber bundle, into a fibration in which you can think of it as a base space and a fiber bundle and so on. That is getting closer to thinking about things like the monster group and the Cayley graph of the monster group, and how that might relate to what's going on here. But let's see.
I would have argued that Sam's project is far more relevant.
Ah, okay, let me show that for a second. Fair enough, fair point. Let's see where we have that. Here we go. You only included one picture in this summary. Okay, well, do you want to, I mean, this is there something you think you can say reasonably quickly, Jonathan, about this?
Oh yeah, okay. So Sam what Sam's project was looking at was, we have a bunch of functionality that I've used to investigate some algebraic consequences of multi-way systems, which essentially work by start from some word in a group and then apply either generators, relations, or axioms to that word and use it to construct a multi-way evolution graph with all of its associated structure. And so one of the things we wanted to know was, what does the multi-way system, what is the space of multi-way system for something like Dinkin diagrams in terms of, in relation to the representation theory of semi-simple Lie algebras? What do those multi-way systems look like? So what you can do is you can, one of the nice things, one of the remarkable things about the representation theory of semi-simple Lie algebras is that the representations can be described purely in terms of this very simple combinatorial data, like Dinkin diagrams, Coxeter diagrams, Weil groups, root systems, things like that. Where each generator of the Weil group is just essentially a hyperplane reflection in the associated root system. So what we could do is we could construct these multi-way systems of Dinkin diagrams by just looking at the generators of the Weil groups and using them to construct multi-way evolution graphs in the conventional way, which is exactly what Sam did here. And that particular diagram is a multi-way evolution graph for a particular Weil group, or it's a subgraph of the full multi-way evolution graph, because the full thing is infinite. But in relation to this particular question, the reason I'm claiming that there's relevance here is because the whole monstrous moonshine conjecture connection exists because there is this non-trivial connection between the monster group in abstract algebra, the theory of modular functions, specifically the J function, and the theory of vertex operator algebras. But the representation theory for vertex operator algebras is actually deeply related to the representation theory of generalized Kac-Moody algebras, which is exactly which is essentially the structure that Sam was investigating here. So this is kind of if we can extend this representation theoretic analysis to deal with these vertex operator algebras, we actually have we have a shot of being able to investigate, if we have a multi-way system whose branch-like structure is obeying a modular symmetry group, and where the growth conditions are such that it can be thought of as being meromorphic in the continuum limit, we can start to investigate, what is the continuum symmetry group that such a multi-way evolution graph would satisfy, and under what conditions would that become the monster group? And so I think this is a
actually, what you're saying is, I mean, from the whole connection with Kac-Moody algebras and so on, that might be a path into coordinatization of certain kinds of branchial spaces, because there is a description of these kinds of things in, this is a case where we've got a branchial space, but there is essentially a kind of algebra-like description of what's going on. Embryonic. Right. We're not sure what
But also in complex analysis, there is a known coordinatization, because if you think of a multi-way evolution graph, in which states are real numbers, as being a way of constructing a sort of a function over the complex numbers, where you're essentially you're constructing multi-valued complex functions by taking basically equivalence classes of real valued functions, then there is a natural way you can coordinatize those systems as well, because multi-way systems based on numbers are fairly easy to coordinatize. And so what the monstrous moonshine conjecture would reduce to, I think, in this way of constructing it, is basically a connection between the canonical coordinatization of these vertex operator algebras as represented by multi-way systems, and the canonical coordinatization of these of these J functions as represented by multi-way systems, which is certainly something worth exploring.
Right. Okay, let's just look at a few more of these questions and just see if there are any others we could address right now. Maybe we need another session here. These are lots of very interesting questions here. Okay, there's a question about if the constants of nature can be calculated mathematically, is the universe itself a machine doing these calculations for us with reality as the result? Oh, that's going to take me a little while to unpack the philosophy of that. There's a question from Martin here. When generating computational hypergraphs, how do you ensure that the algorithm which determines the rendering placement does not interfere with your observations? That's an interesting question. I've worried about this quite a lot. It's, we are but humans observing these things. And yes, we can get confused by that. And I think the best we can do is to try multiple kinds of layout algorithms and so on, and to then try and make measurements which are independent of layout. I mean, for example, all of these things that involve continuum limits, they couldn't care less how the graph is laid out to look at visually, but certainly the way that we get intuition about these graphs does depend on these questions of layout. And yes, this is a thing that I've worried about quite a bit. Let's see. Oh boy. Well, there's a question from Techrific about boy, this may be our end here, because this one is really commenting that the speed of light depends on the medium through which it's traveling. How does one think about rulial space as a medium? Boy, that's complicated. So, the notion of a photon traveling through space-time is presumably a notion of some topological obstruction, some sort of strange twist in space that represents the photon. What is a kind of twist in space in rulial space? What is it even in that's a complicated issue, and we don't know the answer. And maybe it's some special kind of computation. Maybe, I think Jonathan's thought about the possibility that the NP-complete problems, for example, are topological obstructions in rulial space. But this question about the propagation, I mean, that gets really wild and weird. The propagation of an NP-complete problem in rulial space. That's we're a few months away, I'd say, at least. What's interesting in this project is you gradually build up kind of a language and an intuition for talking about different kinds of things. The notion of brachial space, how that works. The notion of what it means to make of quantum observation frames and so on. The notion of generalizing, event horizons to different kinds of spaces and so on. I think we've done less work than we should yet on rulial space. That's probably going to come when we start thinking about deep connections to computational complexity theory and so on. But there are no doubt all kinds of analogies about the propagation of particles in physical space versus the propagation of something in rulial space. We don't understand that yet. So I think this is a comeback in a little while, and hopefully we will have a better understanding of it. And we hope, keep asking these kinds of questions, because this is what's driving this project forward. And we're really excited about the number of people who are getting involved in this, both thinking about some of its philosophical implications and doing the hard physics. And we have a whole lot of experimental physicists who say, just give us an experiment to do and we'll try and do it. We don't have the experiments yet. We really need to do that work, because that's another sort of exciting thing to push on. All right, I think we need to wrap up here. Thanks very much for joining us, and look forward to telling you about future developments in our physics project. So